All right, in this video, we're going to look at vectors in three-dimensional space. And so to begin, let's introduce some terminology. So the real number line, right, just the points on the number line. Well, we're going to denote that using the script R notation. Okay, so R by definition is the set of all real numbers x. Okay, now if we go up a dimension, look at points in the xy plane, okay, we're going to denote that as R2, or R squared in other words, and it consists of all ordered pairs x comma y, where x and y are real numbers, and x and y here are just the coordinates of the various points in the plane. Okay, now if you go up yet another dimension, we're now looking at xyz space, okay, and we'll denote that as R3, or R cubed in other words, and it consists of all ordered triples, x, y, z, where x, y, and z are real numbers, and x, y, and z here are just the coordinates of the various points in space. So for example, let's say I have the point P with coordinates 3, 4, 5. Well, just as we do in the xy plane, okay, if I run from the origin 3 units in the direction of the positive x-axis, 4 units in the direction of the positive y-axis, and 5 units in the direction of the positive z-axis, okay, we wind up at this location P with coordinates 3, 4, 5. Okay, now note, if you look at all points P where the z-coordinate is 0, okay, so this point P in green here is one such point. So x, y, they can be anything they want, right, and the z-coordinate is 0. That describes a plane. It really describes the xy plane. You want to think about just looking down, right, on the plane, and you're really looking at this picture up here. Okay, now if I consider all points P where the y-coordinate is 0, so x and z can vary, but y is fixed to equal 0, we're going to refer to that as the xz plane. So xz plane there in blue. And then likewise, the set of all points P where the x-coordinate is 0. Right? Y and z can be anything they want. That describes what we'll call the yz plane. All right, now these coordinate axes, right, the x, the y, and the z axes, they break up three-dimensional space into really 8 what we'll call octants, right? In the plane, in the xy plane, you have 4 quadrants. In space, you have 8 octants. Okay, now the numbering scheme in the plane, it's quadrant 1, quadrant 2, 3, 4. The numbering scheme in three-dimensional space is not so important, but one octant that tends to get a lot of attention is what we'll call the first octant, and by definition, that consists of all points in space where the x, the y, and the z coordinates are non-negative. Okay, so it's this region in here. Okay, so now let's look to describing vectors in three-dimensional space. So just as we did for vectors in the plane, okay, we'll consider the standard basis vectors, where now we're looking not just at I and j, but also k there. So I, by definition, okay, this is the vector of magnitude 1 that points in the direction of the positive x-axis. J, it's the vector magnitude 1, it points in the direction of the positive y-axis, and likewise k, right, it has magnitude 1 and points in the direction of the positive z-axis. So in component form, I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. Okay, so now thinking about building blocks. Okay, let's say I take 2 of the i's, 3 of the j's, so I just took these 3 j's and I'm going to shift them over here, and then I'm going to take 1 k and I'm going to build this vector v. Okay, so v, the I component, I need 1, 2 i's. Then I need for the j component 1, 2, 3 j's, and then 1 k. And then this vector v runs from the origin out to this point right here. So in terms of the basis vectors, this vector v would be 2i plus 3j plus 1k. And we can write that in component form as just 2, 3, 1, where we're using this angle bracket notation. Okay, so This dashed line you see in the figure, that's just the shadow of the vector v onto the xy plane. All right, now let's compute the magnitude of the vector v. How can we do that? Well, first note, there's this right triangle in the xy plane, right, whose height is 2, whose base is 3, and whose hypotenuse, well, using the Pythagorean theorem, is the square root of 2 squared plus 3 squared. Okay, but now, right, if I look at this right triangle formed where the hypotenuse is the magnitude of v, the height, right, is just the magnitude of k, which is 1, and whose base, right, is the shadow here. If I apply the Pythagorean theorem to it, I'm going to get the root of 2 squared plus 3 squared squared, so that's in other words 2 squared plus 3 squared. Then I'm going to add to it the square of the 1, so there's the plus 1 squared. That's going to give me the square of the hypotenuse. Now if I take square roots, right, the length of the hypotenuse, which is the magnitude of v, is the root of 2 squared plus 3 squared plus 1 squared, and that's root 14. So all together, what we're really saying there is to find the magnitude of a vector in three-dimensional space, we just take the root of the sum of the squares of the components. Pretty simple. All right, now here's another example. Let's say v is the vector 2i plus 4j plus 2k, and w is the vector 5i minus k. Okay, if I want to form this combination negative v plus 2w, well, just as we did with vectors in the plane, right? Negative v, just take the opposite of each component. So negative 2i minus 4j minus 2k plus 2w, well, just double the I and the k components for w, so that'd be 10i minus 2k. And by the way, notice you do not see a j component for w. Well, in component form, we're just saying, well, the j component is 0. Okay, so keep that in mind. All right, now to combine these two expressions, okay, just as you do in combining like terms in algebra, right, for your I components, negative 2i plus 10i, that's 8i. Minus 4j, well, there's no j over here, so it would just be minus 4j. And then minus 2k minus another 2k, that'd be minus 4k. All right, cool. Now let's find the magnitude of this vector minus v plus 2w. One thing to note is that this vector in blue that I get from minus v plus 2w, right, is such that each component is a multiple of 4. So I can factor that 4 out. 4 times the vector 2i minus j minus k. The nice thing about doing this is that if I want to find the magnitude of this vector, okay, what I can do is just take this 4 out of the magnitude, and that will just simplify some of my calculations. So in other words, this is 4 times the magnitude of the vector 2i minus j minus k. As we noted up here, to find the magnitude of this vector, you just take the root of the sum of the squares of the components. So 2 squared plus negative 1 squared plus another negative 1 squared. So the magnitude of negative v plus 2w, that's 4 root 6. And then we'll just note here, more generally, okay, if c is any scalar, to find the magnitude of c times the vector v, okay, the c can come out of the magnitude. However, you'd have to be a little careful. Here the scalar was a positive 4, so it just comes out as 4. But since the magnitude really is, well, a length, right, it has to be non-negative for 1, and the way we compute it in terms of this root, right, if it's going to come out, it can't come out as a negative value, right? It's going to come out as the absolute value. So if c is, say, negative 4, if you pull that out, it's going to come out as a positive 4. And that's it. Okay, so this can help cut down on the size of the numbers in your calculations. Well, that's a good place to stop. We'll pick up with more of this in question 2 on the worksheet. See you there.